Okay, so now we're going to move on to section 4 of chapter 2, where we're going to talk a little bit more about electrons and their role in bonding. So, electrons are the only subatomic particle that are involved in bonding when we're talking about making up a compound of multiple elements. And so, electrons occupy what we call electron shells, also referred to as energy levels. An atom can have up to 7 of these electron shells, and each of the shells can hold a specific number of electrons. How do they fill the shells? Well, the shell that's closest to the nucleus fills first, and the number of electrons that are in each of these shells is dependent on which atom we're talking about. So what we call, even though we can have up to 7 different energy shells or levels outside of the nucleus, the one that has the outermost shell that has electrons in it is what we refer to as the valence shell. A couple other things. So we already mentioned that the first energy shell, or the energy shell that's closest to the nucleus, fills first, and they fill with a maximum number per shell. So the energy level that's closest to the nucleus, or the first shell, can hold a maximum of 2 electrons. Every other energy shell beyond the first energy shell can hold a maximum of 8 electrons. If we have our valence shell, so again, the outermost shell with electrons, full, meaning that it has all 8 electrons, we say that it is chemically stable and not reactive or chemically inert. So this is the case when you look at a periodic table and you look at the column all the way to the right. All of those have 8 electrons in their valence shell, so they're not going to react with any other element or atom, and those would be your noble gases. Okay, so let's do an example, because this is a lot of words, but you're probably not familiar with what I'm talking about. So looking here, we have each one of these rings represents one of those energy levels or those energy shells that we were talking about that are actually holding the electrons. That we have the octet rule, which means that we have 8 electrons in each energy level, with the exception of the first energy level. So if we look at helium, the max number of electrons in that first energy level is 2. So we see that its valence shell actually is full and carries 2 electrons. If we look at neon, which has 10 electrons, we begin filling again the ring closest to the nucleus. Max it can hold is 2 electrons. And then we continue on to a second ring or orbital, where we're going to put the remainder 8 electrons. If we had an element with 11 electrons, we would need to draw a third ring and place that 11th electron out here. So these are some examples of atoms that do not have full valence shells, and because they don't have full valence shells means that they are chemically reactive. So for example, hydrogen, its valence shell right here, it only has 1 electron in it. Again, the max that it can hold, or in order to be full, would be 2 if we're talking about that first energy level. So it has an incomplete valence shell. Carbon is another example. So it has 6 electrons. We filled our first energy level with our 2, which is the max that it can hold. Then we moved on to the second energy level, and we see we only have 4 instead of 8. So technically its valence shell could hold 4 more electrons. Oxygen, same thing. We have 8 electrons. The first 2 go in the first ring, and then we place the remainder in the next ring. So we have 6 electrons in our valence shell right here. Not completely full, so we don't have the octet. We could hold 2 more. If we look at sodium, sodium has 11 electrons, so we fill our innermost shell first. It can hold 2 electrons. We move on to the second energy level, which can hold 8. And then we have to place our 11th electron out in a third orbital over here. So these are chemically reactive elements because elements want their valence shell to be full. So atoms that do not have full valence shells tend to combine with other atoms so that they can fulfill the octet rule and have their valence shell filled. So that leads us to the type of bonds that we have. And when we're talking about bonds, we're always going to be talking about electrons because those are going to be the subatomic particles that are responsible for chemical bonding. We have three general types of bonds. We have covalent bonds. These are the strongest. We have ionic bonds, and we have hydrogen bonds. When we're talking about covalent bonds, we're talking about the electrons are being shared between two atoms. We have two types of covalent bonds. We have a polar covalent bond and a nonpolar covalent bond. If we're talking about a polar covalent bond, we're talking about those electrons being shared equally. If we're talking about a nonpolar covalent bond, they are shared equally. So electrons are shared unequally, and nonpolar is the electrons are shared equally. And again, this is the strongest type of bond that we have. Ionic bonds is another type. We're not sharing electrons at all. Instead, we have attraction between two oppositely charged ions. So one of the atoms is going to completely donate or accept an electron in order to form these ionic bonds. So covalent, again, we're talking about sharing. Ionic, we're talking about the complete transfer of electrons between two different atoms. Hydrogen bonds, these aren't really true bonds. They're the weakest type of bonds we have, and they're just attractions between atoms with partial positive charges and partial negative charges. We're going to talk about all of these in more detail now. So let's begin with ionic bonds. So again, if we're talking about ionic bonds, we're talking about the complete transfer of electrons. So one of the atoms is going to gain the electron or electrons, and the other one is going to donate the electron or the electrons. When an atom gains or loses an electron, it then becomes charged. So that's where we saw before. If we have Cl negative, that means it gained an electron, so it has an extra negative charge. If we have magnesium, we see the positive charge there. That means it's lost 2 electrons. So those two are considered ions because they have charges. So we can call these ions something generic based off of whether or not they bear a negative charge or a positive charge. So if we're talking about an anion, we're talking about it having a net negative charge. So net negative charge. And in order for it to have a net negative charge, that means it had to be the electron acceptor. Because remember, electrons are the negatively charged subatomic particles. If we're talking about a cation bears a net positive charge. In order for these ions to have a net positive charge, they had to give up or donate an electron. When we talk about once we transfer the electrons, so one gains and one loses, and they have these positive charges, one becomes the anion and one becomes the cation, those two ions are attracted to each other. So the opposite charges attract each other, and that's what creates the ionic bond. Most ionic compounds are salts. So a really good example of an ionic bond would be that formed between sodium and chloride, which is commonly known as sodium chloride, which is table salt. So that we see sodium has given up an electron, which is why it bears the positive charge. It's given the electron to chloride, to a chlorine atom. And the chlorine atom now has an extra electron, so it bears the negative charge. So in this case, our sodium ion is a cation, and our chloride ion is an anion. So this is showing you what's happening with the actual electrons when we're talking about table salt. So sodium again is going to donate an electron to a chlorine atom. So if we looked at this, sodium has 11 electrons. So in this case, we have a lone electron out in its valence shell. Chlorine atom, if we look at that, its valence shell has 7 electrons in its outer shell. all of these atoms are going to react with each other until they're stable, meaning that they have a full valence shell. If we look at sodium that has 1 lone electron out in its valence shell and chlorine that has 7 electrons out in the valence shell, it's going to be much easier for sodium to give 1 electron than it would be to gain 7 electrons in order to fulfill its 8 or its octet role in that valence shell. So that's exactly what sodium does. It's going to donate that sole electron that's out here, give it to chlorine. Chlorine needs an extra electron in order to fulfill having 8 electrons in its valence shell. And again, when we're talking about chlorine, how things naturally work, it'd be a lot easier for chlorine to take an electron from another atom than it would be to give away 7 electrons in order to have a full valence shell. So here's what it's showing you after the transfer. We see now that sodium gave away that lone electron out here. This is our new valence shell, and it does have 8, so it fulfills that octet role. If we look at chlorine, this is its valence shell that originally had 7 electrons. Now it has 8, so it's super happy and it's stable. Okay, moving on to covalent bonds. So again, this isn't the complete transfer of an electron. Instead, the 2 atoms are sharing electrons, and the electrons that they're sharing are the electrons that are in the valence shell. So if they're only sharing 1 pair of electrons, we refer to it as a single bond. If they're sharing 2 pairs of electrons, we refer to it as a double bond. And if they're sharing 3 pairs of electrons, it's a triple bond. I mentioned previously that there's 2 types of covalent bonds. You have polar covalent and non-polar covalent. So let's move on. Well, I'll remind you here. So polar covalent bonds are where the electrons are not shared equally, and our non-polar covalent bonds are where they are shared equally. So here's an example of methane, which is CH4. So what happens here is we have 4 hydrogen atoms over here, each with a sole or single electron in its valence shell. So we have 4 hydrogen molecules that come together with carbon in order to form a covalent bond. So hydrogen, because this is the first electron shell, we only need 2 electrons in order for it to be stable or happy. So when they share this pair, hydrogen is fulfilling its maximum amount of electrons in its valence shell, which would be 2, so it's happy. Carbon has 4 electrons in its valence shell, and it needs 4 more in order to fulfill the octet rule. So when we bind to 4 different hydrogens, now we have 8 electrons in the valence shell of carbon, so carbon's happy as well. This is an example of a non-polar covalent bond where the electrons right here that are circled are being shared equally between carbon and hydrogen. So here's just some other examples when we talk about molecular oxygen. Oxygen in our atmosphere does not exist as a single atom. Instead, it is covalently bound to another oxygen molecule. So it would be O2. And you can see 2 oxygens combined together, and they share 2 pairs of electrons, so they form what's called a double bond. And a double bond is kind of drawn like an equal sign. Nitrogen as well combines with another nitrogen molecule in order to fulfill its octet role. So in the case of nitrogen, they're sharing 3 pairs of electrons, and they have a triple bond. So we have 3 dashes between the 2 nitrogens to represent that it's a triple bond and 3 pairs of electrons being shared. So I told you previously that methane is an example of a non-polar covalent bond. So is carbon dioxide. So right here we can see there's a double bond between carbon and oxygen over here, and a double bond between carbon and oxygen here. Those electrons that are within those bonds are shared equally. So if we were to actually look at where the electrons are, they would be directly in the middle between the oxygen and the carbon atom. So if I want to draw them out, it's a double bond, so they're sharing 2 pairs of electrons, or 4 total electrons. So they'd be kind of perfectly aligned between the 2 atoms. polar covalent bonds are different because the electrons that are in the bond are not being shared equally. One of the atoms has a greater ability to attract the electrons because it is what we call more electronegative than the other atom, which would be considered electropositive. So the more electronegative atom is going to pull harder on those electrons in that covalent bond. And when it pulls harder on those electrons, it forms what we call partial charges. Not true charges, but partial charges. So the atom that pulls harder on the electrons ends up bearing a partial negative charge, while the atom that is farthest away from the electrons ends up bearing a partial positive charge. And because we have these two different charges, we say that we have a dipole. So really good example of a polar covalent bond are the bonds between the oxygen and hydrogen atoms in water. So oxygen is more electronegative than hydrogen. So because of that, it's going to pull on the electrons a little bit stronger than that of hydrogen. Because it pulls on those electrons a little bit more, it's going to end up bearing a partial negative, while the hydrogens are going to bear the partial positive. And this just means partial, this symbol right here. So if we were to actually look at this bond and see where the electrons are, we'd see that the electrons are very, very, very close to oxygen and very far away from hydrogen. So because electrons are negatively charged subatomic particles, it causes oxygen to get that partial negative charge. And because they're farther away, the electrons from the hydrogens, they end up getting the partial positive charge. So this is just kind of like an overview of the two different types of bonds when we talk about ionic, polar covalent, and nonpolar covalent. And what it's showing you is distribution of electrons. So again, if we're talking about an ionic bond, we're talking about the complete transfer of electrons. If we're talking about covalent bonds, they're being shared. If they're not being shared equally, that would be a polar covalent bond. If they are being shared equally, that would be a nonpolar covalent bond. And you can see down here we have full charges. If we're talking about an ionic bond, we're talking about a cation or an anion. If we're talking about a polar covalent bond, we're talking about partial positives and partial negatives. And if we're talking about a nonpolar covalent bond, it would be electrically neutral because we don't have any transfer of electrons at all because they're being shared. Okay, so the third type of bond is a hydrogen bond. And again, these aren't really true bonds that are formed. They're very, very, very weak. So what we talk about hydrogen bonds, we're not talking about bonds within the same molecule. So like how we talked about oxygen and water and hydrogen, these are true bonds that make up one water molecule, right? When we're talking about hydrogen bonds, they're not within one water molecule. They're between multiple molecules of something. So for example, if we're talking about another water molecule over here, we can form hydrogen bonds. Let me delete this. We can form a hydrogen bond between right here. So the dashed line right here would represent a hydrogen bond. And again, it's between two different atoms or two different molecules. It's not within the same molecule itself. And how does it form? Well, remember, if we look at our water molecule, we have a partial positive on our hydrogen and a partial negative on our oxygens. So those partial charges are attracted to each other, and their attraction forms what we call hydrogen bonds, which is shown right here. And again, not a true bond. It's common between dipoles, which again is the partial positives and negatives, and they typically form between hydrogen and oxygen or hydrogen and nitrogen. They're also really important, even though they are the weakest type of bond, because they act as intramolecular bonds and they hold things into three-dimensional shapes. So for example, we know probably that our DNA is a double helix, meaning it has two strands of DNA that are held together in a helical fashion. Those two strands are held together by hydrogen bonds. When we talk about the three-dimensional structure of a protein, so it looks globular like what we think of, it's held in that three-dimensional shape by hydrogen bonds. So even though they're really weak, they really hold together a lot of things in our body and are very, very, very important. However, because they are weak, if we were to get a fever, so something like a high temperature above 104, it's going to cause those hydrogen bonds to break and for our proteins to become non-functional. So here's an example of hydrogen bonds being formed, again, between different compounds or molecules. So we see one water here and one water here. We don't have hydrogen bonds within the molecule itself. We have them between different molecules. And the attractions are caused by these polar covalent partial charges. So we cannot form a hydrogen bond in an ionic compound or a non-polar covalent, because again it requires those partial positives and partial negatives and the attraction between those two different atoms bearing those in order to form the hydrogen bond. So this is just kind of a review of things that we went through in the first part of chapter 2. So we talked about the subatomic particles. Those are your protons, electrons, and neutrons, their differences, so where they're located, their weight, and the charge that they carry. We talked about some different terms, atomic number, atomic symbol, mass number, isotopes, and atomic weight. So make sure you can work through that and understand what those are and be able to calculate the number of protons, neutrons, or electrons if given the mass number. We also have reviewed types of mixtures, just have a general understanding of the 3 different types, so colloids, suspensions, and solutions. You also need to know how to make a 1 molar solution, which again is just calculating the molecular weight of the molecule that you're trying to make a 1 molar solution of. And kind of understand what we just went through now when we talk about electrons, the octet rules, with the exception of the first electron shell that only can carry 2 electrons. What the valence shell means, which again is just the outermost energy shell that actually has electrons in it. What it means to be stable. So if it's full, the valence shell is full, then it's stable and unreactive. All atoms and elements want a stable valence to be stable, so they try to fulfill the octet rule, and they do so by forming those 3 different bonds.